So the answer for this quiz is A. But personally, I think it is not as straightforward. The reason is because when I give you an introduction about the interference, the variable time is not considered. But here, because the wavelengths evolve with respect to time, so which means the pattern, the interference pattern, also evolve with respect to time. So no matter at any particular moment, d sine theta is always equivalent to m lambda for the constructive interference. So you can use for the formula for the destructive one, so it doesn't matter. So for any particular moment, this is true. But now the lambda evolve with time, but the distance d is fixed because this is just the separation between the two sources. So when the lambda become bigger and bigger, theta will also become bigger and bigger. So you will find out this interference happen will be the case is that the position happens for the first bright fringe will have higher or the bigger angle. So if originally this is the position of first bright fringe, now it will be here. So therefore, the whole interference pattern will simply be stretched out. When the wavelength is evolved with time, they will just become broader and broader and broader. Okay, so now let me give you examples. So you have the two slits, and now the separation d is given, and for sure a pattern will be created on a screen, and the distance from the screen to the center of the light source, which is capital L here, is given. So now the information is, if the 10th bright fringe above the central fringe is a linear distance 12 cm above, which means this is the position of the 10th fringe, and the distance from here to the central one, it is 12 cm. Based on this information, what is the wavelength of the light? So let me give you a hint. So apparently, if it is the 10th bright fringe, the angle will be much bigger. So what do I mean by the angle? I mean this one. So for the constructive interference, this is a condition, d sine theta equal to m lambda. So if it is 10 and the wavelength is fixed, in this case, wavelength is fixed in this example. So apparently d will be much bigger. So what does it mean? Even though we don't know the wavelength, but we know m is 10, we know the d value. So if you can find out the information about the angle, you can get the wavelength. So this is a hint how to solve the problem. And let me show you the details. So as before, I always suggest you should write down everything we know first. Now let's try to calculate the wavelength. So because for the 10th bright fringe, we know that the y distance from the 10th bright fringe to the central one, this y value, if you use the triangle here, and the angle is theta, theta is unknown, but you know the relation between the y and L. It is simply through the tangent. So L tangent theta will be y. So theta will be arctangent over y over L. So you can use the information given here, the y and L, to calculate the angle, which is actually related to the position the 10th bright fringe happens. Then you are going to use the condition for the constructed interference. But now you are going to calculate the lambda. So originally the equation is m lambda equal to d sine theta, but now you only focus on lambda. And d is 10, the m is 10, but d is the separation also given here. And now the angle is already found out here. So you can calculate that. The wavelength from the source is actually 4.4 multiplied by 10 to negative 7 meter. Now let's look at the second one. So the problem B want you to solve is that now what is the linear distance from the central bright fringe to the 10th dark bright above that? So if you know this is a 10th bright one, not a surprise to you, you will find out this is the 10th dark one. But what is a y value now? So once again, you should use the equation we have learned before. So this is the condition for the dark fringe. So we don't know the theta, but you know the d value. And m is 10, and you know the wavelength. So basically, you can calculate the theta. So what does it mean? If you know the theta, once again, you can use the trigonometry relationship to get the y. So let's see the solutions. So because the condition for the dark fringe is d times sine theta is equivalent to m minus 1/2 multiplied by lambda. So m is 10, and lambda is calculated in the part A, and d is given. So you can calculate the theta for the 10th dark fringe is 2.8. So using the triangle again for the trigonometry relation, now the y, the distance from the 10th dark fringe to the central bright fringe, is L times tangent theta. So L is always fixed, yeah? So now the distance is 0.11 meter to the central one. So now, finally, let's try to study that. I just explained to you that the interference the patterns depend on the path difference. But if now you are interfere with a source which is a reflected waves, then you have to consider one more thing, which is that depending on what kind of reflections, actually there will be a phase change happens. So there are two different kinds of scenario here. So if you have the incident wave from the higher index refractions to the lower index of refractions, so you can consider this is the water or this is the air, just for your visualization. Then when the light was reflected, there's no phase change from a higher index of refraction to a lower index of refractions. But now, if it is from the lower index of refraction to a higher index of refractions, then the reflected wave actually will be out of phase and will be half wavelength out of phase. And actually, we already studied this phenomena before in the chapter 14. So from higher index of refraction to a lower index of refraction, you can consider this is the end, free end. And with a high index of refraction, it is the fixed end. So do you remember that when the wave hit the free end, the wave will propagate and the reflect wave will be in the same phase as the original one. But for the higher index of refraction, it is a fixed end. So originally, the wave will try to drag the material down, but they cannot. So because they cannot drag the material down here, so instead, the wave will be dragged downward. So they will be out of phase. So this is the thing we already studied before. So let's try to summarize what we have learned. So when you try to study the phase change in the reflected wave, then there will be no phase change from the lower index of refractions to there will be no phase change from a higher index of refractions to a lower index of refractions. But from the lower index of refraction to a high index of refraction, there will be a half wavelength phase. So this is second parameter we should understand, the path difference. Now it is the phase change due to the reflections. But very important message is that there is no phase change in the refracted wave. So it only happens for the reflected wave. So this is the very second important physics. So let me give you actually related to the example. So you have two layers of the glass, and you have the ray 1 and ray 2. So apparently the ray 1 will be reflected for the end layer for the first one, and the ray 2 will be reflected for the second layer here. Okay, so if you make the interaction region bigger, then this is the situation. The ray 1 is reflected for the first layer, and the ray 2 is reflected in the second layer. So now we have to calculate two things. So which is the path difference and the phase change. So now I'm going to define a quantity so-called the effective path length. What is the effective path length? It is the effect due to the path difference and also the phase change. So for the ray 2, apparently, they will travel 2 times d further distance. So this is the path difference we just discussed. And you will say it is not D exactly, it is this one plus this one. But you can consider this is a very small region, so we can have approximation that because this is a very short distance and the angle is small, so this distance can be approximate in terms of D. But this is also the reason we use effective. So this one plus this one, you can simply say it is D plus D. So this is the path difference. But for the effective path difference, now you should consider that ray 2 is reflected. So it is from a low index of refraction to a high index of refractions. Here it is the air, this is a glass. So apparently this reflection will cause a phase change, which is 1/2 wavelength. So you may argue that this one also have a reflection between the layer and the glass and the air. And you are right, but there's no phase change here for this layer, for the ray 1. It is because this happens from the high index of refraction to a low index of refractions. I know some of you must be a little bit confused now. So let's try to refresh for our memory. So for the ray 1, this is the case. For the ray 1. For the ray 2, the reflection is for this case. So that's the reason for the ray 2, there's a 1/2 wavelength phase change, but not for the ray 1. But now let's focus on the ray 2. So ray 2 will have the path difference 2D and also the 1/2 wavelength phase change. So the effective path length of the ray 2 is 2D. So now after that, the ray 1 and ray 2 are parallel. So how about the result for the interference? So if the interference is a constructive one, which means this effective path length should be equivalent to the integers of the wavelength. So this term will equivalent to m times lambda. So now if you divide lambda on both ends, you will get this result. Okay? And for the destructive interference, which means now this term will equivalent to m minus 1/2 multiplied by the wavelength. So you divide by the wavelength on both ends. You see, this is the result. So that is how we get the interference pattern for the reflective waves. So they involve in that whether the reflective wave is out of phase or in phase. So finally, we are going to study is that the interference happen in the oil silk or the soap bubble. So not only consider the path difference and the phase change on the reflection, we have to consider the third fact, which is the change in the wavelengths. So let me explain to you why. Because for the ray 1, you will find out this first reflection will have one phase change. But the ray 2, they will propagate into the, for example, the soap bubble. And this one, they will have no phase change. But the wave will propagate at a different velocity there. So the wavelength is different. So let's try to calculate the effective path length for the ray 1 because they have the phase change here. So the effective path length for ray 1 is 1/2 lambda. So this term divided by lambda is 1/2. The effective path length for the ray 2, because there's no phase change here, so they only consider the path travel. So we simply consider the thickness of the soap bubble is T. So therefore, the effective path length for ray 2 is 2T. But when you try to divide the wavelengths, it is not that trivial. This is the wavelength in the bubble. So the wavelength is no longer the same. The wavelength of the light in the medium of the index n, the wavelength lambda m, will be this value. So therefore, if you substitute this value into this formula, then you are going to calculate the path length difference is these terms. So therefore, the condition for the destructive interference is this one, which is this term will be equivalent to half of the wavelength. So which means if you add the 1/2 of wavelength on both ends, you will find out this is the formula for the destructive interference. So now the surprise to you is that is this for the constructive one, this will be the formula. and this